In this video, we are going to see some subspaces of vector spaces. In most important applications in linear algebra, vector spaces occur as subspaces of larger spaces. For instance, we can see that the solution set of homogeneous equations of linear equations in n variable is a subset of Rn. That is, the systems of linear equations is also a subspace of the set of all real numbers with n dimension, Rn. The definition of subspace of a vector space is that a non-empty subset W of a vector space V is called subspace if it satisfies all the rules of operations. In vector space, if we have addition and multiplication, this must satisfy those rules. And also the subspace W must be closed under the operations which are inherited in V. It can be a vector addition, vector multiplication, or ordinary addition, ordinary multiplication. So this should satisfy all those rules. Let's consider the first example, which is a subspace of R3. We can show that the set W, which is a set of ordered pairs x1, 0, x3, where x1 and x3 are real numbers, is a subspace of R3 with the standard operation. The set W is non-empty because it contains the vector 0, 0, 0. Graphically, if the set W is interpreted as simply the xz plane as shown in this figure, W is closed under addition because the sum of any two vectors in the xy plane is also will be a point lying on the xz plane. That is, suppose if x1, 0, x3 and y1, 0, y3 are in W, then their sum will be x1 plus y1, 0, x3 plus y3, which is also in the xz plane. Similarly, we can see that W is closed under scalar multiplication, and also we can verify that the remaining 8 axioms of the vector space is satisfied in this case. Let's take another example, which is a subspace of functions using calculus. Let W5 be the vector space of all functions defined on the closed interval 0, 1. And let W1, W2, W3 and W4 are functions or vector spaces defined as follows. W1 is a set of all polynomial functions defined on the interval 0, 1. W2 is a set of functions that are differentiable in the interval 0, 1. W3 is a set of all functions that are continuous on the interval 0, 1. And W4 is a set of all functions integrable on 0, 1. We can easily show that this W1 is a subset of W5. In fact, we can show that W1 is a subset of W2 and W2 is a subset of W3. W3 is a subset of W4 and W4 is a subset of W5. Let us take the first set W1, which is a set of all polynomial functions defined on the interval 0, 1. So that is our set W1. To start with, we have the set of polynomial functions. We know that every polynomial function is differentiable on the interval 0, 1 using calculus. So this W1 is a subset of W2. W1 is contained in W2. And again, using calculus, we know that every differentiable function is continuous. So when every differentiable function is continuous, W2 will be contained in W3, or W1 is contained in W2 already, and this W2 is contained in W3. Again, using calculus, we know that every continuous function is integrable. So your W3 is contained in W4, where W4 is a integrable function. So W1 is contained in W2, W2 is contained in W3, and W3 in W4. Again, using calculus, we know that every integral function is a function itself. So W4 is contained in W5, and hence W1 contained in W2, contained in W3, contained in W4, which is contained in W5. So in general, if Wi is less than or equal to j, then Wi is contained in Wj. So we have the subspaces of functions as a very good example for vector spaces. So here we have a polynomial function is contained in differentiable function. Differentiable functions are contained in continuous functions, and continuous functions are contained in integrable function, and integrable function W4 is contained in just functions. So all polynomial functions are functions itself. So in this video, we saw some two examples to explain about the subspaces of vector spaces. Hope you enjoyed watching this video. Thank you for watching.